Okay, we saw in class on Tuesday that this series right here I referred to as a geometric series, and we didn't really talk about why. So we're going to start today by talking about what makes this a geometric series. And so in general, the pattern that occurs from one term to the next in a geometric series is that you multiply by some fixed common ratio. So if I multiply 1/2 by, in this case, 1/2, I get the next term 1/4. And if I multiply 1/4 times 1/2, I get 1/8. So for a geometric series, we're going to have a fixed common ratio that we multiply by to get from one term to the next. If we define this more formally down here, so we say a series is geometric if each term is found by multiplying the preceding term by some fixed constant r. And so we get something like you have your starting value. So this is like your first term. In the last example, it happened to be 1/2, but you could start at any value. And then the next term is that first term times r. And then we multiply by r again, right? So we take the previous term, a times r, and we multiply it by another r. That's going to give us a r squared. And so we keep going, and we notice that because the first term wasn't necessarily multiplied by r, when we get to the nth term, a sub n, the nth term is going to only have n minus 1 copies of n that we multiply. Okay, but we're going to just keep repeatedly multiplying by r, repeatedly multiplying by r. Sorry, that was bad timing for a pop-up. Okay, so in general, if we write this in sigma notation, we have some first term a, and then we have r being multiplied by itself repeatedly. Okay, so what I want you to think about when you think about geometric series is, as functions, the actual explicit formula for the geometric sequence, the actual explicit formula, I'm sorry, is really just an exponential function. Remember, these sequences are functions, and so these are just exponential functions. So think of your most favorite exponential function. You have some a value that's like your starting value. In fact, that ends up being your y-intercept, so that hits at a. And then b is the number that you're repeatedly multiplying by, multiplying by, multiplying by. And we know that if b is greater than 1, we have exponential growth. And if b is between 0 and 1, and we talked about this in class, I think last Friday, we had exponential decay. And so actually, in fact, that's really all we have here, except of course for a series, we're going to be adding the terms. And of course, the terms themselves as a sequence would just be the discrete values at the integer values. But again, I just want you to see the parallel between geometric series or geometric sequences and exponential functions, because they really are both the same. It's just repeated multiplication by the same base. So when we then look at the geometric series test, which of course is a test we use only for geometric series to determine if they converge or not, well, we have this test. It says a geometric series converges if the absolute value of r, that's that common ratio, is less than 1. And it diverges if that absolute value of r is greater than or equal to 1. If the series converges, then in fact we can find its sum. It's going to converge to a over 1 minus r. Okay, and again, a is that first term of the series, and r is the common ratio. I do want you to see the parallel here, that if the r value is bigger than 1, right? That's going to correspond to exponential growth. So I'm sorry, I just circled the wrong one. Okay, if the r value is greater than 1, here we go. That's going to be exponential growth. If it's equal to 1, by the way, so if you just keep multiplying, so if you have y equals a times 1 to the x, that's just y equals a. So that's just a horizontal function. If we add up the terms of a constant function like this, we know from the divergence test that would diverge. And certainly if we add up the terms of an increasing function, that is also going to diverge by the divergence test. So the divergence test really could have gotten us this conclusion, that if you keep multiplying by something bigger than 1, the terms are going to get larger, and so the series is going to diverge. What we didn't get from the divergence test is this condition, that if in fact the base is, or the ratio is less than 1, or its absolute value is less than 1, then in fact we have convergence. Okay, and this is going to correspond more to the decay situation, except we do allow for our base to be negative. Okay, but the base still has to be I keep getting pop-ups. The base still has to be between 0 and 1. So if the absolute value of r is less than -1, we're looking at values between -1 and 1, right? Those are values that have an absolute value between -1 and 1. So again, that's going to correspond to, if we allow for negative values, that's going to correspond to the exponential decay. Okay, so keeping this in mind, that if in fact, if the absolute value of r is less than 1, we get convergence, and further, we know what it converges to. It's going to converge to this. So which of the following geometric series converge? So let's just scroll down a little bit. Okay, and if they do converge, we're asked to find their sum. So let's look at this, and first of all, just realize this is in fact geometric. If it is helpful to you, I still recommend writing out the first several terms. So when n is 1, so a1, when n is 1, I replace n with 1. This is just function notation. I get 4 to the 0, so I get the term 5. Okay, then when I write the next term, a sub 2, I'm going to get 5 over 4 to the 2 minus 1, so 4 to the 1, so that's just going to be to the 4, so 5/4. And then I write the next term, it's going to be 5 over 4 squared, so 16. Okay, and it's just going to keep going like this, so this is going to be whatever 4 cubed is. And so what I want to notice here is that to get from one term to the next, so to get from 5 to 5/4, I would have to multiply by 1/4. If I wanted to get from 5/4 to 5/16, I'd have to multiply by another 1/4. And so I'm getting this common ratio that every time I'm going to be multiplying by 1/4. So in fact, that tells me right here that my common ratio is 1/4. Okay, so since the common ratio is 1/4, and I know the absolute value of 1/4 is less than 1, I know that this series converges by the geometric series test. It converges by the geometric series. Okay, geometric series test. Sorry, I just had to pause the video. And so in fact, we know what it converges to. The sum, it converges to a, which is the first term, so that's 5, over 1 minus r, and r in this case is 1/4. So that's the same thing as 5 over 3/4, or 5 times 4/3. So the sum is 20/3. So we would say that this series converges to 20/3. And what we mean by converges to 20/3 is that if you were to add up all infinitely many terms of this series, the result is a finite number. We get 20/3. Okay, let's look at the next example. Again, if you're finding it useful, or if you're having a hard time seeing that this is a geometric series, again, when you're asking yourself, is this geometric or not, think about exponential. If you go back to this previous example, what I see right here is in the denominator, I've got 4 to a power, right? So this looks like my base, where my base, and again, the 4 is in the denominator to a power, n minus 1, but still a power. So my ratio must be, sorry, that 4 looks like a 9. I'm repeatedly multiplying my denominator by a 4, by a 4, by a 4, right? So in the denominator, multiplying by a 4 is going to be 1/4. I've got my exponential decay. Over here, I'm seeing I've got 3/2 to the n. So if I write out the terms of this series, this is 3/2 to the first, 3/2 to the second, 3/2 to the third, etc. So again, to get from one term to the next, we're repeatedly multiplying by 3/2. So we can see this, it's exponential. See that base? The base is the ratio, that's 3/2. So the absolute value of 3/2, that's our r, in fact is greater than 1. So this series diverges by the geometric series test. Okay, moving on to the next example. Hopefully right away you see this is an exponential function. This is a geometric series, and we see that r is -1/3. If you are not able to see this, then I would recommend writing out the terms like we did and look to see if you're multiplying by a consistent value every time, a constant ratio. It can't be changing from one term to the next. It has to be a constant ratio. In this case, r is -1/3. The absolute value of -1/3 is certainly less than 1. So we know that this series converges, and it converges to a over 1 minus r, right? So in this case, that convergence is going to be the first term, and I'll go back to that in a second, over 1 minus r. Okay, so what is a? Remember, a is the first term. So what you're doing is you're taking whatever this starting value is, and you're replacing it in for n. So our first term is just going to be negative 1/3. Okay, so we evaluate this. We get negative 1/3 divided by 4/3, which is the same thing as negative 1/3 times 3/4. In other words, the sum converges to negative 1/4. Okay, let's look at one more example. Here you got to be a little bit careful because notice that both the negative 1 is being raised to the n power and 4 is being raised to the n power. So I could write this as like 5. I'll just leave the 5 sort of out front by itself. And then I see it's the negative 1 over 4 that's being raised to the n. Also something to note out, which is why we have this asterisk here, is that the starting value of the index doesn't always have to be 1. It can be anything, including 0. That's going to play a role in finding our first term. Okay, so when I look at it this way, I can really see that that's my base of my exponential or my common ratio. If I can't see that, or if you're struggling at all with this, again, write out those terms and then look to see what can you multiply to get from one term to the next. If it's not constant, it's not geometric. But in this case, r is clearly negative 1/4. And since the absolute value of negative 1/4 is less than 1, we know that this series converges by the geometric series test. Oops, that's a dot. And so what does it converge to? It converges to, in the denominator is going to be 1 minus r, so 1 minus negative 1/4. And the first term is whatever we get when we plug this lower index value in for n. 5 times negative 1/4 to the 0, that's actually just going to give me 5. So my sum is 5 over 1 plus 1/4, so that's 5/4, which is 5 times 4/5, or 4. Okay, now of course we can only apply the geometric series test to a geometric series. So the big question here is, can you identify if a series is geometric? And again, I want to just remind you that you're really just asking yourself, is this function exponential if I were writing it as a function? Okay, so let's look through these. We've got 2 to the n over 3. So maybe pause the video or ask yourself, do you think that's exponential or not? Okay, and the answer is yes. So this is geometric. The value that I'm repeatedly multiplying by, the thing that's going to be, that has a base, that r, that's 2 in this case. While we're at it, let's write down the first term because we would need that if we were finding the sum. If I were to substitute 0 in for n here, there, now I can see it. If I were to place 0 in for n, I would get 2 to the 0, or 1 over 3. So my first term is 1/3. And again, if you were not able to identify this as geometric, I would say just write these terms out. If you write out the first few terms, you see that when you go from 1/3 to 2/3 to 2/3 to 4/3, we're always multiplying by 2. All right, next up, let's look at this one. Again, I would recommend pausing the video so that you can really think about whether you think this is geometric or not. This one is geometric, and the common ratio is, you're not just multiplying by 2 repeatedly, you're also multiplying by a negative 1 repeatedly. See, notice that I could write this numerator as negative 2 to the n. So my r is negative 2, and this divided by 4 would just be kind of like the last example, stay fixed. Now, because this ratio is greater than 1, this series would diverge. So I don't really need to know what a is, but if I did, a would just be whatever happens when I put 1 in for n. So it would be negative 2 over 4, or negative 1/2. All right, moving on to the next one. Again, pause the video and ask yourself, do you think this is a geometric series or not? Okay, and actually it is not geometric. Okay, it's not geometric because while the numerator actually is exponential, the denominator is a linear term, it's just n. So if I look at the first few terms, I've got 7 to the first over 1, plus 7 squared over 2, plus 7 cubed, I don't know what that is, over 3, plus, and as I move through this, oops, that wasn't supposed to be a line. Yeah, the numerator I'm multiplying by 7, that's true, but I'm not, there's nothing I can multiply by to get from 1 to 2 and then have that same number from 2 to 3. So this one's not geometric. Okay, pause the video and look at the next one. This one is again not geometric. And I'm not sure if this was clear to you, but this is because we, of course, have n factorial being raised to the nth power. So in fact, you could think of this as n factorial over 2 to the, over just 2, sorry, all to the n. So you might have been fooled for a second by seeing the to the n power, but this isn't just a constant being raised to the n. You've got a changing variable in the numerator being raised to the n. So this one's not geometric. All right, finally, this last example, again, pause the video and predict what you think it is. This one is geometric, and that's because, of course, this is exponential. It's just staring at us, right? We've got this base r being raised to the n power. So r is pi over 4, and our first term, a, is what we get when we put 0 in for n. So 1/4 to the 0 power is 1. So this converges, and those are those values. Okay, so now you're ready to do homework 12.